now. And if you would, please take it away.
Thanks, Chris, and hi, everybody. It's kind of surreal to be in daylight and making vBrownbag and drinking tea rather than something a little bit stronger. I'm usually the host of the APAC edition of the vBrownbag, and many of you know me from hanging out at the vBrownbag stage at the various conferences that we cover. So I've got a piece of the Elasticity and Scalability section, which is Module 1 of this AWS Solutions Architect Associate exam. Like Chris Williams, who presented the last series, I use the aCloud Guru videos in order to study for and pass the exam. In fact, Chris and I were studying in parallel 8 time zones apart, and even took the exam on the same day and both passed it that day, which was kind of nice. So one of my top tips for studying is actually to have somebody to study with, to have a kick-ass buddy, as one of my slides says, and have somebody to just encourage you to continue at it, because sometimes it can get to be a bit of a slog and the life gets in the way and you kind of focus on other things instead. But today I'm going to head into this elasticity and scalability section, and particularly the pieces that we're going to look at are the 4 kind of core services that are about scaling. Making your application scale up and down and affecting some of that. In particular, also with AWS, there is this idea around these 12-factor applications and that you want to have small decoupled pieces. We're going to look at 2 ways of decoupling. One is the simple queue service, and the other is the elastic load balancer. And a larger application that's doing something for a business is going to be made up of a series of smaller applications that are decoupled from one another using these 2 techniques. We'll look at AutoScaling, which usually sits behind either a queue or a load balancer and allows us to scale out our application as the workload increases and then scale it back in again as the workload decreases. And then as a final element of scalability, we'll look at CloudFront, which is AWS's content distribution tool for bringing your web content out close to the users and reducing latency. So first off, what is this elasticity thing? The NIST definition of cloud talks about rapid elasticity, and it particularly says that I've screwed up my slide, that we need things that can be rapidly provisioned and released in this elasticity component of a cloud definition, and the ability to rapidly scale outwards and then back inwards when demand changes. And it ties up with the fact that our cloud resources are only billed for the time that we're using them rather than being a permanently billed thing. So if our demand for resource scales up, it makes sense to buy more resource because presumably we're earning more because the demand has gone up. But when that demand drops off again, scaling back in is critical because we want to pay less when there is less demand. And one of the things that's a characteristic in these elastic services is that it appears that there is unlimited resource available behind the application. And those of us who were playing with Pokemon Go when it was really new found that there were some boundaries on the scalability of the services that they were using, and they've clearly put some resource limits, and those resource limits led to performance issues along the way. So scalability in general comes in 2 forms, and this is a generic thing, it's not necessarily an AWS specific thing, that we can either scale up, as in have a single instance of something and make it a much bigger instance. And in the context that we're talking about here, that's generally EC2 compute instances. We're generally talking about what we would consider to be a virtual machine, but AWS calls an instance. And scaling up involves turning off your current instance and buying a bigger instance with more CPU, more memory, faster disk capacity, those kinds of things, and more network throughput as well as you get the bigger instances. Scale up is one way of approaching scaling a system, but it is very intrusive on AWS. There is no capability to hot add more CPU and memory resources to an instance that's running on EC2. You actually have to destroy the instance and start a new one, usually with the same images, with the same EBS volumes attached in order to scale up. But there's also limits on that. The largest EC2 instance is still not particularly massive. It's not tiny, but it's not a vast thing. A more usual pattern in web applications is to scale out, to have lots and lots of EC2 instances all running the same application and joined together to run that application with a greater aggregate resource. Now we may still use the largest EC2 instance we can get and then run 100 of those, or we may use a smaller instance, but we can combine scale up and scale out. Mostly scale out is much more dynamic because we can start a new instance and dispose of it if we don't need it. We write the applications to suit that. These scale-out collections of virtual machines that we'll be looking at need to be able to get work in some way, and the two classic ways to get work to this group of EC2 instances is the queue service, SQS, and the load balancer. So we'll start by looking at the queue service, and its objective is to allow us to queue up units of work. And SQS is typically used where there is a time lag between, or where we can have a time lag between requesting the piece of work to be done and needing a response. So SQS is no good for responding to a web. You send an HTTP GET request, put it in a queue, well, the GET's going to time out. The web browser is going to say, well, I got no answer. But it can be a really good way of sending a job to be done. So, for instance, if we update on a website, this is my new address. That request goes into the queue, and something else later goes and changes the database. And by later, it could be 3 seconds later, it could be 15 seconds later. We're not talking about a week later, generally. The SQS request goes in, some worker process goes and processes it and says, yes, that job is complete. And this is the objective with the queue, is to decouple the website where I've said I want to update my address from the actual process of updating it, because in the back end there may be 8 different places that this address has to be updated, and we don't want the website to be waiting for those 8 things to update. Instead, the request goes into the queue, and sometime later the queue activity gets completed. The object in the queue is a chunk of text, and the maximum size is 1/4 megabyte of text. Now usually the text is in something like a JSON format where it's very easily machine readable. It's not really intended to be human readable, but it could be JSON or XML in this message. And then one of the characteristics of an SQS queue is that every message will be processed at least once. Now most messages will be processed exactly once. One worker process will pull the message out of the queue, process it, and then delete it. But it is possible for a single message item to be processed multiple times, and that's something that may come up in the exam and is an important part of designing an application as well. It shouldn't cause an error if a message is pulled from the queue, partially processed and the process fails, and then that same message is pulled again. And that should not cause a problem. And then the other thing to be aware of with SQS is that it is a regional scope. So its scope is not just a single availability zone, and instead its scope is in the complete region. So maybe US Oregon or the US East for the Virginia region, or down my way in Australian East in Sydney. That means that the things that are pulling messages out, which is often an EC2 instance, can be across multiple availability zones, and the queue itself is available across all of the zones. And so a zone failure isn't going to cause a queue failure. But if we need the same queue to exist across multiple regions, so maybe we need a global queue, we're going to have to think about how we architect that, because the queue itself is regional, and you might have to have some other process that spreads across a broader scope if your application requires it. So what's the process for creating an SQS queue? Well, you name it. Of course, you've got a region in which it operates, and then you've got a series of timeouts. And these timeouts are significant things that you may get questions about in the exam. It's important to understand what they are. So we'll go through those timeouts. The first timeout is that, or the first concept to have in the queue is that messages live in the queue until they're deleted. And the delete should happen only if processing is complete. We then have some points about the visibility of a message. So an application puts a message into the queue. There can be a delay. We can say make the message in the queue invisible for a minimum period of time, and it may be that we have an application where messages go into multiple queues and you want them to be processed in one queue first and then later in another, and so you would set a timeout for that. The other time that messages are invisible is when something pulls a message out of the queue. It doesn't actually pull it out of the queue, so it makes a copy of that message to itself, and the queue makes the message invisible for a period of time. And I'll just pop back a slide, and you can see the default visibility timeout entry here, the first of the timeouts set for 30 seconds. It needs to be long enough that if things go right, this timeout won't expire while the work is being done. So if the work is simply update my address in one database, 30 seconds is plenty of time. But if this queue is used to transcode media files that are being uploaded, then the transcode may take 5, 10, 15 minutes, might take half an hour. We need the default visibility timeout to be greater than the processing time for the hardest message we've got. We still need it to have as short a time as possible, because if the process that's handling this message crashes and never actually completes and never deletes the message, then this timeout has to expire before anything else can see that the message is in the queue and needs to be processed. Next thing to be aware of is SQS is designed for relatively short-term storage of these messages. And you can see the second one, the message retention period of 4 days. This is the longest time a message can live in the queue. So if we've got a very deep queue that we're processing with very cheap spot instances, and they have to do a lot of work, maybe it's a media transcoding, but we only need it to be finished by the end of the month. We may have very cheap instances that don't run terribly often, and therefore messages may live in the queue for a long period of time. The maximum period of time a message can possibly live in SQ is 14 days. We expect messages to live a much shorter period of time, usually minutes, maybe hours in a queue, but you can have queues that run for a long time. The next part of the settings on the queue is around the polling of the queue. So one side of the queue is the messages coming in, the other side is them being pulled out and something doing the work. There are a couple of different ways we can do the polling. The polling is essentially the application asks the queue, have you got anything that needs work done on it? Is there anything in the queue? And there are two ways it can be done. So the first one is what's called short polling. And the application queries the queue and says, hey, have you got anything for me now? The queue says yes, here's a job, or it says no, come back later. And then sometime later the application comes back and says, hey, have you got anything for me now? This happens on a cyclic basis, and it adds a latency to processing. So if we're waiting for that update of my address in the database, if I've got a short poll and the application only checks every 15 minutes, then it could take 15 minutes from me telling the website to update my address before the database is actually updated with my new address. And that's probably not very desirable. Short polling is great if there are almost always messages in the queue, so almost every request goes in and says, what have I got to do? Here's something to do. But if there are only infrequent messages in the queue, maybe 6 messages a day come into the queue, then short polling is going to either lead to lots and lots of polling of the queue or long delays while we wait for that polling to occur. So there's this thing called long polling. With long polling, the thing that's consuming the queue, the application that's pulling messages out of the queue, can say, hey, let me know when the next message comes up. So if the queue is currently empty, it can sit there for a while and say, let me know, just send me the message when the next one turns up. And there's a timeout for that, which is much longer. It's not milliseconds, it's multiple seconds that this long polling can take. Really good if you need to rapidly respond to an infrequent message, and that's what long polling is for. The application that's consuming the queue has to be configured for long polling. It's not the queue itself that's configured, although we do set a maximum timeout for that long polling. The queue itself is really simple to set up. There was just that one screen with some timeouts on it, and that's all there is to setting up the queue. The hard part in the queue is setting up the application to feed data into it and the application that pulls messages out of it. Again, that's developer enablement. This is just a tool for a developer to build an application. So visibility time, time to process the message. Retention time, how long can a message stay in the queue? Delivery delay is when a new message goes into the queue, how long do we wait? And then the receive message wait time. Those are the keywords that mean long polling when you're asked about it in the exam. So the second decoupling tool is the Elastic Load Balancer, or ELB. We've all come across network load balancers before. We're used to them being pretty static in configuration. The ELB, because it's elastic, is designed to work much more flexibly. The general expectation is that the ELB will spread web requests, although it can be other network protocols, across a group of EC2 instances that then run some kind of web application. ELB, like SQS, is a regional service, so it's within a particular region, and the load balancer is across multiple instances, across multiple availability zones. And this is where we get some of that resiliency in your application, that you have your EC2 instances spread across 2 or 3 availability zones, but all fronted by a single elastic load balancer, a single DNS name that you can access the application through. ELB itself doesn't have its own component in the management portal. You configure it as part of the EC2. So you can see that expectation that we're network load balancing a group of EC2 instances. And the load balancer, unlike something like an F5, doesn't have its own IP address. It really does work through a DNS function. So it has a DNS name, and that DNS name will then point back to the IP addresses of the EC2 instances as you use in the load balancer. One of the things that's really fun for it is that it will translate TCP ports, so you can have the load balancer listening on maybe port 80 and forwarding requests to port 81 on your web servers. And the other characteristic about it, the load balancer, is you can either have it configured to be an internal load balancer that is just used within your application, so allows you to go for requests from one component of your application to another component of your application, or you can have it as an external. You can have it as the front end to access your website or your a component of your application that's visible across the internet. And so if this is an internal component with the application, you're going to constrain down where it can be accessed to, usually to just your VPC, whereas if it's available from the internet, you can have access from anywhere. Configuration from an ELB is a little bit more complicated than setting up a queue, but on the other hand, it just fronts a web service. It's much simpler to consume. So we name it, and then we specify what network protocols this particular load balancer is going to work with. And here we can see it's just a straight web load balancer that I've set up, and it accepts requests using HTTP on port 80 and forwards them to my EC2 instances on the same port. And that's the simplest configuration, but as you can see, flexibility, different ports are allowed, and we can have additional ports in here, and that would particularly be useful if it wasn't just a website. If it was just a website, you probably want HTTPS as well as HTTP, but if it was an application that was running across these EC2 instances that used a group of ports, you could absolutely load balance a group of ports. In addition to specifying the ports that are going to be load balanced, that essentially the ELB is going to listen for, you also need to set up the security group on it. And the security group is essentially a 4-tuple or 5-tuple firewall. So you're saying connections into the ELB on these protocols from these subnets. And this is where it becomes an internal versus external, as we can constrain it down here. And again, you could specify a different set of ports for the internal versus external access. So we've got a source of anywhere is allowed in on HTTP, and we may have some other ports that are used only by other parts of our application internally. So we've got a question in here from Graham. Is ELB essentially HA proxy? It works fairly similarly. It is just a network load distribution tool, and it really doesn't do a lot more than round robin the connections through. There isn't advanced load distribution across your instances the way that you see in some of the other load balancers. Because the way that we're checking to see whether a particular EC2 instance is useful to us is through this health check. This is the way we identify whether an EC2 instance is available or not. We're not going to see any settings in here that are about the load on a particular EC2 instance. We'll actually use AutoScaling groups to back these ELB load balancers in order to deal with load and to scale out. So the health check essentially says, how am I going to identify that a particular EC2 instance is fit to receive requests? The default is that we're going to make a connection on HTTP and we're going to pull a particular HTTP request. And then at the bottom you can see we've got some timeouts on it. So we want to receive a success for this HTTP GET within 5 seconds, and we want to run a test every 30 seconds. You can see an unhealthy threshold, so if 2 consecutive requests are a fail, then the EC2 instance is considered to be unavailable and is removed from the load balancer. So it's going to take 60 seconds of failure, 30 to 60 seconds of failure, before we're going to take an instance out, and that's the maximum time that a failed instance should stay in our ELB based on these settings. Now obviously they're entirely configurable. The other thing to notice is that the healthy threshold is 10 intervals by default, so 10 times 30 seconds, 5 minutes. Right? Your new EC2 instance that's just started up or that's recovered from a failure, we're not going to use it for 5 minutes, and that one can be quite confusing when you first set this up, and particularly in the lab environment. 5 minutes is an awful long time to wait for your EC2 instance to be up, and that's 5 minutes after the web server has started before ELB is going to consider it to be healthy. If you're labbing this, you'll usually set that healthy threshold back down to something like 2, and you may well make the interval more aggressive, like 15 seconds, in order to more rapidly see things happening. But the defaults are probably fairly good for production. You want to be very sure that an instance is up before you actually consider it should be used, and you also expect that you want to fail an instance fairly fast if it stops responding. Of course, you don't want to be too aggressive on the interval, because this is all more HTTP requests hitting your EC2 instances. Next step in the wizard to create the ELB is to say which EC2 instances you want to use. Now, when I set this up, I was lazy and only created a single web server. You can see the instance name. If I had more instances in this region, then I would see more instances here. And you can see that I've got cross-zone load balancing. If I had web servers in multiple availability zones within my region, then I'd get them all showing up in here, and I'd be able to load balance across the group of availability zones, and that helps us with the failure of a single AZ or a single data center. This is definitely the kind of architecture that you want in order to survive larger failures. But there can be even larger failures. It's not entirely unknown for Amazon to lose entire regions. We've seen some instances where the snows of winter have dealt with the entire US East region, and the whole region has been lost. In another section of the set, we're going to look at Route 53, and Route 53 is the DNS service that you would use to set up availability beyond a single region to give you a global availability. Okay, so you would have a series of ELB instances, and your Route 53 would point to the ELB, and that will provide availability for a particular region, but Route 53 would give you your global availability. And here's the end of our wizard. It says, let's just go ahead and create this ELB load balancer, and my instances would start responding on the DNS name that was allocated when it was created. The default domain name for your ELB is pretty long and unfriendly. You can put more friendly domain names on it. You can add your own. Next thing we want to look at is auto-scaling. So we either have a queue which is sending relatively slow requests in to get some work done, or we have a load balancer which is sending the much faster requests in. Behind both of these, you'll usually have an auto-scaling group that allows us to have a small number of virtual machines, a small number of instances, while we've got a small load, and a much larger collection of instances when we have a high load environment. And the auto-scaling groups let us scale out when there's too high a load on the instances we have, and then scale back in when the load is lower. Auto-scaling is made up of two separate pieces. The first piece is a launch configuration. You can see on the top right, it says step 1, create launch configuration. Launch configuration is, here is how to create a new instance for me. And then the second piece is the scaling group. The scaling group and the policies for the scaling group is when to do that. Okay, so the launch configuration is what to do, and the scaling policies are when to do it. So we'll start with the launch configuration. Launch configuration is going to be essentially, here's how you create an EC2 instance for me. Mostly you'll use a custom AMI, so you will have started with one of the provided instance images, which is the boot image, and then customized it with your application. And you use this image. You don't have to. You can use some of the launch tools that you'll see when we create EC2 instances to run a script that makes this machine useful for your application. But if your application is anything more complicated than just install a couple of packages and copy in some files, you're probably going to want a custom image for it, and you can use a custom AMI or a standard AMI. The next thing that we need when we're creating another EC2 instance is what instance size do I want? Do I want a T3 micro? Do I want something with a bit more CPU? Do I want something with more memory, or is this a GPU application? Now, what instance do I want? And then you specify the IAM role, so the security in there, and specify whether additional storage is to be attached, and then create the security group configuration, the network configuration. It's exactly the same process as if you were creating a single instance. You're just creating a template for multiple instances. One of the things I found most confusing about this was that the launch configuration, once you've created it, you can't edit it. So if I need to upgrade my application that's part of this AutoScaling group, I have to create a new launch configuration using a new image. So I've created an updated image that's got my new application. I can't just tell my existing launch configuration to use the new image. I have to create a new launch configuration. I thought that was a little bit of a pain. When we then carry on through into the AutoScaling group itself, then we're getting into more of the region-specific information. Where are my VMs going to be created? And so we'll have this AutoScaling group details that's created after we've done the launch configuration. It says, where do I place these instances and how many of them am I going to have? So we name it, we have a group size. What's the minimum number of instances that I want to start with before the AutoScaling kicks in? And then we specify network configuration. So first off, which virtual private cloud within this region do I want it to be in? And then within that virtual private cloud, what subnets do I want to have? And you'll usually want to have your virtual machine spread across all of the subnets within your virtual private cloud in order to get the biggest redundancy, because of course you can only have a subnet inside a single availability zone. To be able to cope with an AZ failure, you need the VM spread across multiple AZs. And that's what we've done here. I've got just the default VPC and the 3 AZs that are in US West. Having said what instances to create and where to create them, I need to specify some scaling policies. The default scaling is fixed size. So when on that previous screen I said, give me 3 instances and it's going to spread them across those 3 AZs, that's what I'm going to have. That's all I'm going to have. It's not going to respond to load. You probably don't want that in any kind of application that's going to have peaks and troughs in load. What you're going to want is the auto-scaling, where you can specify the maximum and minimum number of instances and then set some alarms to increase and decrease the group size. So the alarms themselves are, geez, I'm blanking on the name. I'm fairly sure it's CloudWatch that does the alarms. And we can attach an alarm to a particular auto-scaling group and use it to scale up and down. So here's a typical alarm. It is CloudWatch alarm, and it says when the, in this case, average CPU utilization exceeds 90% for at least 5 minutes, then trigger this alarm. You can choose to send a notification to a notification service queue. You probably won't. In this case, you're probably not going to want to know that the auto-scaling group has got larger or smaller by one instance. You may want to, but probably not. Probably you're going to want it to go and do this by itself without talking to you. On the other hand, you also want to monitor just how much this is changing, because of course if your auto-scaling group is set to a maximum size of 100 instances and your workload really needs 120, you want to be noticed that it's redlining at 100%. But that's not the purpose of this alarm. This alarm is about creating an additional instance. Or if I'd said if the CPU utilization is below 60%, then I'd use it to delete machines. So we create the alarms and then we specify actions. So you can see here I've got that same alarm, high CPU utilization, and I'm using that to add one instance to my AutoScaling group. And then at the bottom I've defined a separate alarm, low CPU utilization, where CPU utilization is below 30. Remove one of the instances, and that scale back in is important to avoid your bill blowing out as more and more instances are created. Okay, so your autoscaling policies you can change after the autoscaling group is created. There's also on this same screen there is a minimum and maximum instance count, and that's again constrains what your cost is going to be, but also constrains your maximum performance. So autoscaling groups will create and destroy new virtual machines for you, new instances, and they will respond to the load. One of the things to be aware of is that these alarms here are the things that are going to cause VMs to be created and deleted, and it's really important that you tune them carefully. I mean, it may be that the right thing to do in here is instead of adding one instance when CPU utilization goes up, because I've got 3 availability zones, I might want to add 3 instances. And there will definitely be some questions in the exam around how do you achieve a minimum level of performance and availability. The sorts of things you get is questions about if you've got a different number of availability zones inside a region, how do you configure the numbers of virtual machines so that if you lose an availability zone, you still have performance? And that's a really important design consideration around these auto-scaling groups. And that, as I've repeatedly said, that scaling back down again once the workload decreases is really important. So the last thing that I'm going to cover is CloudFront, which is AWS's content distribution network. And the objective of CloudFront is to get a cache of your content, your web content, close to your users. Not really terribly important within the US. The latency to get from one side of the US to the other is not huge. But down where I live in New Zealand, on the end of our wet piece of string kind of internet connections, the speed of light comes into play, and it takes quite a lot of milliseconds for data to get from even the western US down here to New Zealand. The world is a big place. Speed of light limits latency or causes latency, and there is no way to fix that latency other than moving things closer, and that's what CloudFront does. Moves a copy of your web content close to your users. CloudFront is one of the very few AWS services that is global in its scope, so it's not constrained to an availability zone or a region. It doesn't actually operate inside an availability zone or a region. It operates in the edge locations. Those are the data centers where your network connection comes in or internet feeds come into AWS. The edge locations are not the data centers where all of AWS's computers that we use for EC2 instances run. They typically belong to co-location operators, your telcos and the hosting centers. And in these edge locations, we'll have the CloudFront servers. They're one of the few sets of servers that go in the edge locations, and they provide that caching. The configuration for CloudFront has 2 areas of configuration. So you have an origin and a distribution. The origin is where we're going to get the content from. So typical origins for CloudFront would be an S3 bucket. If we've configured an S3 bucket as a static website, then we can use CloudFront to accelerate access to that. Just checking out this question from Graham. So it's not availability zone based. How is availability guaranteed for CloudFront? CloudFront will put your data into caching locations in front of the final location. If those caching locations fail, so if a particular edge data center fails, then the content is still available from the primary central location, and DNS failover essentially will handle that in front of CloudFront. It's the same for all content delivery networks, is that there is a disposable cache of the data distributed out, and the primary copy of the data lives in a central data center. The disposable cache is used to speed access, but should it be available, the primary data from the central data center is used. Okay. So our origins are where that primary data center sits. We usually expect that we'll either have an S3 bucket or a load balancer, an ELB, as the destination for CloudFront. However, we could have a single EC2 instance as the origin for a CloudFront distribution as well. We could have a web service sitting inside an EC2 instance. And the other thing that we can have is a Route 53. That's the DNS service that AWS runs. We could have a Route 53 configuration as the origin. And that then allows us to use CloudFront to act as a content distribution network for any kind of content, because Route 53 can point to servers that are outside of AWS. So we could use Route 53 to point to web servers across our data center, and then use CloudFront to point to that Route 53 and cache our own content all across the world. And as Graham said, it slows down. So if there has been a failure of that edge location that has the CloudFront, then absolutely things will slow down. In fact, the first access to a resource that is protected with CloudFront will still be slow because it's a cache. It doesn't aggressively go out. CloudFront won't go to your application and pull data out to the edge locations or wait for the first user request, and will cache every user request piece, and there's a limited size to that cache, and as new requests come through, the oldest data will fall out of the cache. So yeah, there is an acceleration goes on, but it's not every single request. The first request for data through a particular edge location will still be slow. The next thing that we configure for CloudFront is a distribution, and this is the locations that we're going to distribute this content to. The more CloudFront locations you distribute your content to, the greater the cost. The fewer, then the less caching you get, and therefore the greater chance of a slow experience for the user. So the distribution, each distribution has its own URL, and it can be a web page, or it can be real-time media streaming, so the RTMP media streaming. RTMP being really important if, for instance, you are a cloud guru and you're distributing real-time video that is being streamed out from some central data center, and that's where the RTMP media streaming caching can be really useful for CloudFront. Each distribution can have multiple origins. So we could have an S3 bucket that contains our media, but we could have EC2 instances that provide the actual web services, and then we have some regex that says if the request is for an MP4 file, pull it from the S3 bucket. But if it's for a PHP, HTTP GET on a PHP file, then pull it from the EC2 instance that's running a LAMP stack. So we can have different content coming from different places, and that can get fairly complicated. In particular, it's complicated for the updates because, of course, you're updating content in two different places. Yeah, ends up being fairly cool. There are some really cool things you can do with CloudFront around locking down specific content and requiring client-side certificates before particular content can be accessed, and that's often used for internal enablement training that's still internet delivered but only accessible to staff within your organization. There's some really nice controls around that with CloudFront. The objective with CloudFront is to make your application more responsive by caching data close to where your users are and avoiding those speed of light problems with getting around the world. So the general summary for this elasticity and scalability section. You can scale up an EC2 instance, and consequently something like an RDS database server can be scaled up by simply using a larger EC2 instance. It's a relatively low boundary on this, and it's a very intrusive thing to scale up. So we typically work with a scale out configuration for applications that can scale out. It uses AutoScaling, which is a part of the EC2 configuration. It's a combination of two parts, a launch configuration which says this is how to build the instance you need. Here is the AMI, the instance size, and the rest of the security configuration around it. And then there are the alarms that say this is when to create these new instances, when to fire off the launch config. The alarms are CloudWatch alarms, and they should be used to both scale up and to scale back down again your group of EC2 instances. The other crucial part in the scalability is your application should be designed to decouple the components within the application. And the typical decoupling methods are the simple queue service, which passes a message into a queue, and sometime later that queued message gets processed. Or elastic load balancer, which queues requests and immediately, or distributes, doesn't queue, ELB, distributes requests across a group, typically of web servers, but it can be other services. The other way to get scalability is to get the data close to your users through CloudFront, or to address some of the scalability limitations, in particular with ELB, by using Route 53 to get your DNS naming across multiple regions. All right, that is my content. I, of course, then have a slide that tells me I have gone too far, and that the last slide was a summary. I should have stopped there. I think we've hit the questions along the way. Chris, did that seem reasonably clear to you?
Very, very. And
Cool, excellent.
I have not seen any other questions from any other sources, and I believe you've answered all of Graham's questions, Alastair.
I really appreciate, Graham, that you actually asked some questions, and that's always nice to get some feedback that people are playing along at home, and so I do recommend asking questions as we go. All right, well, this has been the module on the AWS Solutions Architect Associate exam around elasticity and scalability. I'm Alastair Cooke, and I'll hand back to Chris to close us out.
Thanks, Alastair, and thanks for a great presentation. In keeping with the those that came before you, it was absolutely fascinating.
It's a really interesting subject area. I really enjoyed studying for this exam, and I'm considering whether I should do the professional one or whether I should do some of the other associate ones.
The thing that has impressed me as much as any of the other elements is the way you and all the other presenters have used the real world examples. That's what makes it even more interesting for me.
Well, you know, Chris, that the origins for vBrownbag is all around the people who have to build and support things, and we live in the real world and we feel the real pain. It's very seldom that we get into the marketing architecture slides.
Do we have one more question? No. Excellent presentation. Thanks from Graham, and thank you, Graham. I don't see any other questions. I'm checking the other sources. Nope. I think that's it. Thanks, Alastair.
Absolutely a pleasure.
I'm going to stop the recording now.